As I've mentioned in previous videos, from a mechanics perspective, pretty much all you need to describe the motion of anything is Newton's laws of motion and kinematics. However, there's a lot of situations where this becomes a computationally intractable problem. For instance, if we think about something like having a bike wheel spin, like so. It mentioned before that the reason it spins is because as the axle is churning, as the axle's churning, the spokes, by Newton's first law of motion, as the axle increases its rotation rate, the spokes, by Newton's first law of motion, want to keep going at the rate they were. And so what happens is greatly exaggerated. Instead of the spokes being nice and straight like we think they are, when the wheel is actually rotating, the spokes curve back a little bit. And I am greatly exaggerating the curve for the purposes of clarity here. So then the spoke wants to return back to its original shape, thus grabbing onto a chunk of the rim right here and accelerating the rim. And so as you mash down on the pedals and make the hub of the bike wheel turn faster, you wind up bending the bike spokes and making the rim go forward. Now, even within that, you have to repeat the same analysis within the rim. Looking at the rim, you would actually have to repeat this exact same kind of analysis molecule by molecule within the rim. And so what happens is that the bonds between adjacent molecules get stretched, like so. And again, you've got this same kind of twisted back shape like we saw with the spokes. Now, the way spokes are designed versus the way a rim is designed, the spokes will flex a lot more than the rim typically. But even within this, the rim is flexing. And the same analysis can be done with the interface of the chain to the sprocket, to the cogs on the cassette that's attached to the hub, between the cassette and the hub, the whole bit. So the key thing here is that there is no rotation without deformation. Without deformation. Now, if that deformation is important to you, you're in a bit of a pickle. To do it completely 100% correctly, you would have to set up Newton's laws of motion for each and every atom in the entire bike wheel. And that's going to be a royal pain to solve that collection of interconnected systems. However, it turns out that for a lot of objects, we look at the bike wheel, unless you are a professional cyclist who is riding a very specially engineered bike wheel that's designed to have as little mass as possible and give you exactly the performance you need to, say, go up a mountain in a major bike race or something like that, you're probably never going to visibly see that the spokes bent, or for that matter, that the spokes got a little longer. Because remember, as you're picking up speed, each chunk of the rim needs something to be providing a centripetal force. So not only are the spokes bent back, but they're getting longer so that we have a tension force pulling in on the spoke as well, like so. Be that as it may, if you're a company that's designing bike wheels for professional cyclists, you probably are going to have to worry about the fact that the spokes are getting curved back and that they're getting longer, both mostly because you're trying to minimize the weight, and you're also trying to keep the clearance between the bike wheel and the back of the bike as small as possible for aerodynamics reasons. But if you're not a professional cyclist, or you're not an engineer working for a company designing equipment for professional cyclists, that bending and flexing isn't going to matter. And so then you won't feel the need to have to resort to doing what's called finite element analysis, where you actually model this as a whole bunch of mass points that are connected with springs in a computer and let the computer sit and crank on it. So if that's what you have to do, that's what you have to do. But a lot of the times we don't care. You look at the bike wheel and go, looks like the spokes are straight to me, looks like they're the same length to me. But we know that deep in our heart of hearts, that's not quite true. It's bent back a tiny bit. The spokes are a tiny bit longer, but not so much that we notice, and not so much that it matters for our calculations. So that, in a nutshell, is the rigid body model. In the rigid body model, ODEL. In the rigid body model, we know in our heart of hearts that there's deformation. But we pretend it doesn't happen anyway. And a lot of times this is fine. If we can do that, and it's a proof of this is beyond the scope of this treatment, but you can look on my series of classical mechanics videos. It's usually proven in a advanced upper level undergraduate classical mechanics course that in a situation like this, you can completely describe, if we can model the object as a rigid body where we pretend the deformation isn't happening, it turns out you can completely describe the motion. Completely describe the motion as the translation with the translation of the object's center of mass combined with its rotation about its center of mass. Now, this means we're going to have to define center of mass, which is where we're going with the rest of this video. But that turns out to be all you need to do. For instance, if you take an object like a ruler, grab it by its end and give it a bit of a toss. What you'll probably find happen is as the ruler flies in the air, it's maybe doing something like this. In case of the ruler, the center of mass of the ruler is located at its physical center. And this is really lousy artwork, so I'm just going to say you'll observe that this motion is a parabola. And then combined with this, you have an independent rotation happening about this middle point on the ruler. So you can separate out the parabolic motion of the center of mass, boop, like that, and then say we add to that the object's rotation about its center of mass, like so. And that if the object can be modeled as rigid, that completely 100% describes the motion of the object. Worst case, so this takes you down from needing something on the order of a mole of variables, so say 10 to the 23rd variables, to represent the x, y, and z position of every single atom and molecule, down to worst case scenario 6 variables. At absolute worst, you'll need 3 variables to describe the translation of the center of mass and 3 to describe the rotation. So I'll say that this is the worst case. Three translation variables plus 3 rotation variables. And you only need as many as 3 rotation variables when you've got an object that's tumbling. If it's a more smooth rotation like you probably had if you decide to actually toss the ruler and watch the motion for yourself, you'll find that more typically the translation can be collapsed down from 3 variables to 2 for motion in a plane. And you only need 1 rotation variable if the object is not tumbling. So, worst case scenario, you went from about 10 to the 23rd variables down to 6. In a more typical case, and we'll start with the more typical case, you'll have gone from 10 to the 23rd variables down to about 3. Either way, I count that as a win. So if you care about the deformation, then you can't pretend that it's not happening, obviously. And then you'll have to go ahead and model this as a whole bunch of points. Now, even the best computers out there aren't going to be able to do it molecule by molecule. There just isn't enough computer memory to store 10 to the 23rd variables. However, you may be able to get away with modeling it as only a few billion points of mass connected with springs or something like that, and get a very satisfactory numerical simulation. But at the end of the day, you're not going to be able to do it exactly no matter what, just because there are way too many variables to deal with. And if you don't care about the deformation, if it's small enough that it doesn't matter for what you're concerned with, then instead of taking it from 10 to the 23rd variables down to a billion or so, you're taking it from down to 6 or even 3. And instead of writing horrendous computer code, you can just do some straightforward algebra and calculus. So again, that's a big win if the situation will allow you to do that. Unfortunately, there are many situations where you are. So there you go. So let's start with defining the center of mass. Let's start on a fresh page. There we go. So it will turn out that the most convenient definition of the center of mass is to literally do a weighted average, and this is where the term weighted average actually comes from, of the positions of all the particles. So this big M here is the mass of the whole object. And then what you're going to do is you're going to sum over all of the particles the mass of the particle times the position of the particle. And if you've kind of forgotten your summation notation, just real quick, I always just think of this as a for loop, so I'll just write a very short stub of C over here if this helps to remind you. If you're not familiar with computer programming languages, not a big deal. But I would be doing something like saying for I equals 1, I less than or equal to n, where n is the number of particles, increment I. Whoops, my bad. Oh, my syntax sucks today. Let's do that a little better. There we go. Now my curly brace. So we would say M, we'll call it MR. We'll just make that equal to 0. Oops. 0.0, right? So then we can just say MR plus equals MI R I, or and if we're just, yeah, and we'll close that out. I know you don't technically need the curly brace if it's a single line, but just deal with it. And then we can just say RCM equals MR over big M. If you want, we can calculate big M while we're at it. You can say M equals 0.0, and then inside the loop, we can say big M plus equals MI, if that helps you. If it doesn't, not a big deal. But basically, all this is saying is take molecule number 1, take its mass, times it by its position. Take molecule number 2, take its mass, times it by its position, add that to what you found for molecule number 1. Take molecule number 3, take its mass, times it by its position, add that to what you found for molecules 1 and 2. So forth and so forth and so forth until you run out of molecules. Then, after you're done with all of that, divide by the mass of the whole thing. So that's what the summation notation means. It turns out that with this definition, the velocity of the center of mass and the position of the center of mass can fall out from, or do what you think they should. So by that I mean, we can say that the velocity of the center of mass is equal to dr, the time derivative of the position of the center of mass. Well, that'll be d dt of 1 over m times the sum. So then I can pull out the 1 over m because it's a constant. And since I'm applying this to a sum of things, I can sum the derivatives. That's perfectly fine. And since each of these m's individually is a constant, I can pull them out of the derivative. Oops. And then you look at it and say, oh, hey, that's the time derivative of the position of the individual particle. So what we get at the end of this is that with this definition of center of mass, here, let me put a nice box around it. There we go. With that definition of center of mass, we end up getting that the velocity of the center of mass is the weighted average of all of the velocities of all of the constituent particles. And you can repeat this analysis one more time by differentiating it one more time to get that the acceleration of the center of mass is the weighted average of the accelerations of all of the constituent particles. So this works out really handy. This is saying that we can treat the center, as far as analyzing the translation goes, we can treat the center of mass of the object as just a single point mass, and we can do all the kinematics and dynamics things we've ever done with it before, because the acceleration of the center of mass is simply the time derivative of the velocity of the center of mass, and same between velocity and position. And nicely, it just turns out that we get that the position of the center of mass is the weighted average of the positions, the velocity of the center of mass is the weighted average of the velocities, and the acceleration of the center of mass is the weighted average of the accelerations. So that seems really, really handy. So just to kind of make this all concrete here, let's just say you had A, B, C. Let's just say we stuck our origin over here. There's my position of object A. There's my position for object B. That's my position vector for object C. And the center of mass, once I crank it through, it'll be somewhere inside the triangle bounded by these 3 points. I'll just mark it with a crosshair here. And this would be the position of the center of mass of these 3 objects. So one of the things we see is that the center of mass can just be in some arbitrary point in space. It doesn't have to be anywhere on an object even. It can just be in some region that's bounded by the object, even if the object itself doesn't occupy any space there. As an example, just think about a donut. The center of mass of a perfect donut is in the center of the hole of the donut. There's no donut there, but that's where the center of mass of the donut is. So, with this definition of center of mass, we can make Newton's second law work in a reasonable way. We'll be able to say that the net force on the system will be equal to the mass of the thing times the acceleration of the center of mass of the system. So the net force on the system is going to be equal to the sum of the net forces on each of the constituent particles. And this is going to go on for a very long time. But what we can do is we can say, okay, the net force on object number 1 will be the external forces acting on object 1 plus the force of object 2 on object number 1 plus the force of object 3 on object number 1 plus and such. Same thing for the net force on object 2. It'll be the external forces acting on object 2 plus the force of object number 1 acting on object number 2 plus the force of object number 3 acting on object number 2 plus and such. And then we can continue this game. F net 3 will be the external forces acting on object 3 plus the force of object 1 acting on object 3 plus the force of object 2 acting on object 3 plus and such. So what we're imagining here is, say, maybe it's gravity. Let's just, so if this is object 1, this is object 2, this is object 3. This would be my external force on object 1. And then similarly, this would be my external force on object 2, and this is my external force on object 3. Say we're near the surface of the Earth and gravity's just pulling straight down. And if these things are interacting together, let's just say that objects 1 and let's just say they're all attracting each other, but they could also be repelling. It wouldn't matter. To hold the system together, if this is a rigid object, we would have a force of object 2 on object 1, probably an electric force between adjacent atoms. Object 1 on object 2, like so. And then similar. F3 on 1, F1 on 3, and then finally F3 on 2 and F2 on, well, that's turning into a mess, sorry. And then this is finally F2 on 3, like so. All right. Well, here's the thing. I can go ahead, I claim that I can cancel these two off against each other. I can cancel these two off against each other. And I can cancel these two off against each other. Why am I allowed to do that? Pause the video and get back with me. Okay. The reason I am allowed to do that is because the F2 on 1 and 1 on 2 are a third law pair. So that means that F1 on 2 equals F2 on 1 in magnitude, but it has the opposite direction, making it a negative. Similarly, 3 on 1 and 1 on 3 are a third law pair, and 3 on 2, on 3 on 2 and 2 on 3 are also a third law pair. So this one will equal minus F2 on 3. And finally, this one will equal minus F1 on 3. So all the internal force pairs cancel. This was something we were using intuitively earlier when we came up with things like thinking about the problem of how much tension is there in ropes that are connecting a whole bunch of objects together in a train. And we played a game of nesting the systems because we'd realized that we had never really cared about it. But now we've proven it, that the net force on the object will just be the sum of the external forces on the object, and the internal force pairs cancel. So now let's take this one step further. So we're left now with this being just the external force on object 1 plus the external force on object 2 plus the external forces on object 3 plus and such. Okay. By Newton's second law, since this is the same difference as the net force on object number 1, so my bad. Let me back up just a second here. So it's equal to that. But now if we go back to what we had right here by star, this line here, this is equal to the net force on object. This sum here is equal to the sum of the net forces. Well, F net 1 is equal to M1 A1 by Newton's second law. F net 2 is equal to M2 A2 by Newton's second law. F net 3 is equal to M3 A3 by Newton's second law, and so forth. So that's what this is, but we also worked out that this is what this is here. Okay. So this gives us that we have, if I want, I can multiply and divide by the mass of the system. So this is just a fancy way of writing the number 1. But by doing this, I'll have M1A1 plus M2A2 plus M3A3. There we go. Plus and such. This bit right here is the acceleration of the center of mass. So the net force on the system, the sum of all of the external forces on the system, is equal to the mass of the system times the acceleration of the center of mass of the system. So the big deal here is that Newton's third law works for an extended body if we treat the center of mass as it's allowing us to treat the center of mass as a geometric point that feels the effect of all of the forces acting on the system. Now, so far, this much is true even if we say that the object is not rigid, but we're still just keeping in mind that we're probably going to be thinking about a rigid object. Okay. So, as far as finding the center of mass goes, now we've shown that Newton's second law works for it. Remember that we said RCM is equal to 1 over the mass times the weighted average of the positions. Well, we can take x, y, and if need be, z components of this. So the x-coordinate of the center of mass is going to work out to be m1 x1 plus m2 x2 plus m3 x3 plus and such over the total mass of the system, which is m1 plus m2 plus m3 and so forth. And then similarly for y and z. So for instance, just to do a very straightforward example, there we go, I'm just popping in a coordinate system. Let's just say we've got 3 point masses making up my system. We'll say that I have, this is a y equal, so this is y here, this is 1 meter, this is 1 meter, that's x. And then we got one object at the origin here. So we'll say that the mass of object number 1, let's make it 2 kilograms. We'll say the mass of object number 2 is 4 kilograms. Let's say it's 1, 2, 1. 1 kilogram, 2 kilograms. Mass of object 3 is 1 kilogram. I'd like to find the center of mass. Well, it lives entirely in the x, y plane. So right off, we can just write that z, the center mass of z is 0 because the z coordinate of all of these is 0. So, yeah. And now let's go ahead and find the center, the x component center mass. That'll be 1 kilogram. Well, object 1 has an x coordinate of 0. Object 2 has a mass of 2 kilograms and an x coordinate of 0. Object 3 has a mass of 1 kilogram and x-coordinate of 1 meter. And we'll divide that by 1 kilogram plus 2 kilograms plus 1 kilogram. Well, 0 plus 0 plus 1 over 4. So this will be at plus 0.25 meters. And similarly for the y coordinate of the center of mass, this will be 1 kilogram times, here the y coordinate is 1 meter, and the other two are 0. So it's again located at plus 1/4 of a meter. So the center of mass would be about right there for that system. All right. Now you might ask, what if the object is extended? So in general, what you would have to do, let's say there's your coordinate system and you got some horrendous blobby looking thing like this. What you would have to do is imagine tiling this up into a whole bunch of differential pieces of mass, dm. And then you would have to say that the location of the center of mass can be found. Well, still officially, what you're really doing is still summing over I. So maybe I should go and take a look at first like this and say we're picking out individual atoms here. So again, we could start with the same thing. This is my ith piece of mass here. So we could start by saying, okay, it's 1 over the mass of the whole thing times sum over I, mi, ri. But if we got like 10 to the 23rd objects or so, there's a cheat we can do. We can approximate the sum with an integral, which I know sounds weird because usually you think of the integrals of things as being more exact. But in this case, it's actually the sum that's the exact thing because you're adding up over the individual atoms. However, what you can do is you can kind of give up on the idea of individual atoms if you're standing far enough away from something. For instance, if you look at a beach, if you're far enough away from the beach, you can't tell that there are individual grains of sand. It just looks like, beach. You get close enough to it, you can tell there's individual grains of sand. And so again, that's the same kind of deal. If you're close enough to this that you can see the individual molecules, then you're probably going to have to do a sum. But if you're far enough away that you can't see the individual molecules, which frankly is most of the time, what we can do is we can imagine just treating this as a continuous blob of stuff. And then instead of us having individual masses, we say the mass of this region is dm. And then we go ahead and say that the center of mass of my extended system is 1 over the mass times the integral of the RCM there, of the position over my differential pieces of mass. Now the thing is you're going to have to turn this into a dx, dy, dz somehow. And since I'm trying to avoid doing any particularly nasty integrations, I'm just going to say this is what you would do in general for some random object. Now, it'll turn out that as long as the object is kind of nice, for instance, if the mass isn't changing as a function of position, if it's a uniform object and the object has some sort of symmetry to it, the center of mass will be located at its symmetry center. So I'll say often center of mass will be at symmetry center. And even if you have objects that don't look like they would be polite enough to do that, say if you've got some sort of L-shaped piece of sheet metal like this, what you can do is you can imagine cutting this up into pieces you understand better. So for instance, you could cut it up into 3 pieces like this, and then you go ahead and treat each of these smaller pieces as a point mass at its center of mass that you find by saying, oh, it's at the symmetry center. And then you find the weighted average like that. You could even decide to save yourself a little bit of grief, and instead of breaking it into 3 squares, you could break it into a square and a rectangle. So here, all of these would be the same mass. I'll just call it M. So it'd be M and 2M. So okay, a little more bookkeeping, but 2 terms instead of 1. And then here's the weird one that you could do. And this is handy for if you've got problems where you're punching a hole out of something. Is you could instead imagine that the object is combined of an object of mass 4M located at the symmetry, with the center mass located at the symmetry center. And then what you do is you imagine adding to it. So stack on top of it a mass of negative M. And yeah, I know that physically doesn't make any sense. This is a mathematical trick. So you say that you'd have a mass of negative M located here. And although you can't have an actual physical object of mass M, mathematically, of negative M, mathematically you can pretend you do. And it'll work, and this will also work just fine. All 3 of these will give the same coordinates for the center of mass. All right, that was quite a bit there, but that will get us started with the translation of the center of mass. In the next video, we'll define moments of inertia in order to help describe the rotation about the center of mass. So we'll catch you over in the next video.